welcome to 9.9. We still miss you so much. We're just crying about how much we wish that you were sitting here in our classrooms with us right now. It's very sad to be here all alone. Isn't it very sad?
It is.
Anyway, but we're going to do our best. So, representations of functions by power series basically is we're just continuing on with what we've been learning. Let's go. Okay. So, remember Busani's first video where she talked about how 1 over 1 minus x was the answer to a geometric series, and the geometric series that she was talking about was, hold on, x to the n. And that's a geometric series that converges with geometric series. Converges for absolute value of x less than 1. Do I need to write the terms out? No. You can go back and look at her video. She's got all the terms written out. Super important that we realize that anything that's in this form, or even kind of close to this form, can be written as a geometric series. So what we're going to do today is just try to alter things that sort of look like this to make them really look like this, and then change them into sigma notation. Note, we could do this the super long way also, and I'm going to remind you what the super long way was without doing it. Originally what we did back in the beginning of 9.7 was we took our function, we did all these derivatives. In my class we called it yoga because it was sort of soothing. We did all the derivatives, we plugged in the center, and then we wrote a big giant polynomial that approximated something like this. It was never a polynomial, but it approximated a rational function or sine or cosine or e or log. We did it for all those things. And you can still do that, right? That would be fine. But this is so much faster. So we're trying to find really fast ways to find a polynomial or series approximations of functions that aren't polynomials. And so we're just trying to get you shortcuts. The long cut still works. So here's my first question for Ms. Busani is, can you alter this in a way that looks like a number? So ultimately, I'm going to draw something over here that's sort of like a framework. Ultimately, we want to have something, cloud, over 1 minus something else. Because that would be, then we could say that's equal to, I should have made more room, the sum of the first term, cloud, times heart to the n. That's a geometric series. So can you make this look like that?
So I guess if it's,
Starting with the trick, this is hard.
negative x minus 1, then for the heart and 4 for the cloud.
Sort of, but the thing is, as soon as you put x minus 1 in there, you're changing the center, and we need our center to be 0. And so I shouldn't have started off with this problem. This was too hard for us because this is mean. The first thing I'm going to do is divide everything by 2. And so what I need you to know is this is the first thing that you have to do. First things first. You've got to get a 1 there. And for you to get a 1 there, you've got to make this thing be a 1. So I'm going to turn these around, and I'm going to re-ask you the question, and then it's going to be easier. So this is 2 over 1 plus x over 2. Now,
oh, well now the part is just negative x over 2.
Okay, so I'm going to write it 2 over 1 minus negative x over 2. And is the center still 0? It is, and this is why. Because whatever's in this little parenthesis blob has to have an x minus 2 if the center is 2, or an x minus 0 if the center is 0. And this does not have an x minus anything, so that's x minus 0 for our center. So now I'm going to erase this word because it's in my way. I'm going to now do my cloud over 1 minus heart, and we can see that this is going to be the sum of 2 times negative x over 2 to the n as a geometric series. Does that make sense?
Yeah.
Okay. And better yet, because we kind of like to know whether something's alternating, I'm going to pull out my negative 1 and make it 2 times x over 2 to the n, like that. And there you have a series that approximates this rational function in the interval, what interval? So where does this converge?
Well, it's gotta be where x over 2, the absolute value of x over 2 is less than 1.
And when is that?
So from negative 2 to 2.
And do I need to check endpoints?
No, because it's geometric.
Yay! So that's it. So no endpoint check. Not checking endpoints. All right, good. So you can stop right here if you're like kind of losing your mind on what are we doing? Like I've lost my focus. And what you can do that would help you to regain your focus is to put this into your calculator as y1, and then as y2, write out some terms of this, and maybe we should write out some terms to this. This geometric series, always, for this to be the sum, it always has to start at n equals 0. So let's generate some series for the people at home who want to put this in their calculator.
Cool.
So when n is 0, what is our first term?
2.
Well, wait, we have an x though, because we don't know what x is.
No, but x over 2 to the 0 is going to be 1.
Oh, you're right. Oh, you're right. It's 2. Okay. What's the next term? I'm going to let you do this. I'm not even going to wonder if you're right. Minus?
Negative 2, negative x.
Okay, I'm leaving it like this. But yes, negative x. Okay. Sorry about the sideways writing, everybody. I'm really sorry. I ran out of space. I didn't plan this ahead.
All right, so plus,
This is n equals 2, right?
yeah, so 2 times x squared over 4.
Okay, you guys can do more, right? You can do more, but this, it's gonna like whittle down to a really nice equation, like 2 minus x plus x squared over 2, and all the denominators will be cute, and maybe not, because, yeah, they will, because they'll have 2's on the top and powers of 2 on the bottom. Okay, anyway, so if you're like, what are we doing, why, I want you to graph this, and then I want you to graph this, y1, y2, and look at them, and see that they are really close to each other on the interval from negative 2 to 2, and then outside of that, wacko, because that wacko means diverges. Got it?
Cool. Yeah, and let's pause there and we'll make a new video.